Bismillahirrahmanirrahim. Assalamu alaikum. Here I am going to explain to you about unit operation 2 binary distillation of ethanol and water mixture. I am going to explain to you step-by-step data analysis of this experiment. First of all, you have the raw data, which is for the shown here, bubble cap and fact column. Okay. Let me remind, in this experiment we are studying the binary distillation of ethanol water mixture. Okay, and we are doing it in two different types of column, bubble cap column and fact column. Okay, so if you have seen the demonstration video, we first conduct the experiment for the bubble cap column. We allow the system to reach steady state, and then we collect samples, okay, from the top, bottom, and the feed, and run it and characterize it by gas chromatography. So from the GC analysis, I will show you in the later step, we can find out the composition. Similarly, in the second part, we do the experiment by using fact column, okay, and again after reaching the steady state, we collect the samples and analyze it by gas chromatography and find out the compositions. Okay, so this is the raw data. The bubble cap, for example, you know the feed the temperatures of the different stages here. Okay, tray column, and here you know the reflux ratio. So you know F02, the reflux and distillate, and the reflux ratio will be F02 or F03 2.05. These are the important things. That's why I have highlighted it. Similarly, you need to know the feed temperature, which is around 86 degrees Celsius. Okay, and you also need to know about the cooling water flow rate, which is around 350 liters per hour, mentioned here. Yeah, 320 liters per hour. Okay, similarly for the packed column, you know the reflux ratio, you know the feed temperature, which is around 86, and the cooling water flow rate here. Okay, this sheets below shows the GC analysis or the gas chromatography. Okay, so this is this stream says UO2 feed. Okay, and here you see the two peaks. One is for the ethanol and water, and we should be expecting these peaks because it is a binary mixture consisting of ethanol and water. Okay, so there are two peaks, one for the ethanol and one for the water, and here you can see the corresponding areas of these peaks. I'm using double screen, so I cannot see it clearly, but I'm sure you will be able to see it clearly once you open it fully on your own computer. Okay, ethanol peak is around 19 point something, and the water area is around 86%. Okay, similarly, you see here UO2 bottom for the tray column. So in the bottom product, we will be expecting high amount of water because ethanol is a light product, so it will be on the top. So that's why we have a small peak for ethanol and we have a larger peak for the water. And again, you can see the area of ethanol smaller and the area of water around 94, which is way higher. Okay. Similarly, for the top and the tray column, you have ethanol peak bigger than the water. That's why the reason for this is that we have ethanol higher concentration in the top product. Okay, and you can see the corresponding areas for the ethanol 89%, and for the water it is around 10 or 11%. Okay, similarly you have the top product for the packed column and the bottom product for the packed column. The feed remains the same for both. Okay, so using the gas chromatographic results, we will first of all find out the compositions. Moreover, you are given the vapor liquid equilibrium data, VLE data, in your manual, so in form of the mole fraction. So you plot the VLE data. Number two, we will use the GC results to find out the composition. So for this purpose, we will find out the area ratio of each stream. For example, for the feed, we will find the area of ethanol or the area of water. This will give you a numerical value. Similarly, for the top product, we will find the area ratio again, area of ethanol or area of water, and similarly for the bottom product. In all cases, we will divide the area of ethanol by the area of water. Then you will use the calibration curve to convert the mole ratio to to convert the area ratio to mole ratio. Okay, so the calibration curve is provided in the manual, or you can just simply use this equation. Mole ratio is equal to this constant 0.3737 multiplied by the area ratio. So by this way, you will convert all the area ratios to the mole ratio of the feed, the top product, and the bottom product respectively. Converted the mole ratios, the area ratio into mole ratio, then you can easily convert the mole ratio into mole fraction by using the relationship mole fraction is equal to mole ratio by 1 plus mole ratio. So you convert the feed, the top and the bottom mole ratios into mole fractions. You will also need to convert the mole ratio in the feed to mass fraction of the feed by using the average molecular weight of the mixture, because you will need it for the enthalpy diagram. Okay, so once you complete this table, then The next part is to find out the value of the Q. In this calculations or in this experiment, we feed the mixture as saturated liquid, but still you can confirm it. So the value of Q is given by this equation, which is HV minus HF divided by HV minus HL. HV is enthalpy of saturated vapor, HL enthalpy of saturated liquid, and HF is the enthalpy of the feed at the feed temperatures, for example 86. Okay, so using the enthalpy diagram given in your manual, later on I will provide you a link of a YouTube video where you can learn. I'm sure you know it, but just as a reminder for you, you can review that lecture on the YouTube to find out how to use the enthalpy diagram to find out the enthalpy of the vapor, feed, and the liquid. Okay, saturated vapor, saturated liquid, and vapor. Once you do this procedure, you will find that the value of Q is nearly 1.95, 0.96 sometimes, depending upon the feed temperature. Okay, so you can have the Q line equation. Okay, now coming towards the McCabe-Thiele diagram, you can see that we have the square. Okay, first of all, we'll draw the 45 line this way, and we'll here locate composition for example the bottom, the feed, and the top. Okay, so once you locate this point by x equal to y line or the 45 line, of course this is the equilibrium data. Okay, now first of all, the top line, it starts from xd, and we have the equation of the top line, y equal to r by r plus 1 times xn plus xd by r plus 1. This is a straight line, so we can draw it by slope or by intercept because we know the first point. The intercept is given by xd by r plus 1, so we can simply, we know from our raw data, we know the reflux ratio, and we know xd from here, the top. Okay, so once you look at the intercept, let's say it comes out here 0.5, 0.25, whatever you have value, so you have 1 point here and 1 point xd. You can simply connect these two lines by a straight line. Okay, the next is the feed line or the Q line, which you can draw it by using this equation, or if it is nearly equal to 1, you can safely draw a straight or perpendicular line. Okay, so this is Q equal to 1, you have a straight line, a perpendicular line, sorry. Once you draw the top line and the Q line, then it is very easy to draw the stripping line or the bottom line. It is basically from the intersection of these two lines to the XB. So your McCabe-Thiele diagram is complete, and now you can do the stepping to find out the number of trays. Okay, here it says if Q equal to 1, simply a perpendicular line. If Q is very less than 1, maybe 0.8 or 0.7, then you can use 2 points. For example, you have 1 point as XF, and the second point you can find out by this equation. Okay, here we do not use the slope because, or we can use the slope, we cannot use the intercept because the intercept will lie outside the scope of this graph. So draw the operating lines and find the optimum feed location. You can find the optimum feed location at the stage which is crossing the feed line. Okay. Number 6 in this calculation is to find out the minimum reflux ratio. We can find out the minimum reflux ratio by drawing a line through the pinch point. Okay, again in the McCabe diagram. So this is the 45 line. This is the equilibrium line, and the Q line, if it is a perpendicular, you can draw a straight line up. Okay, now the intersection of the equilibrium data and the Q line is called the pinch point. Okay, so if you draw a line from XD passing through the pinch point, okay, this line, so you start from XD and draw the line passing it through the pinch point and extend it to the y-intercept. Now this is the line of minimum reflux. So from this line, either from the slope or from the y-intercept, you can find out the minimum reflux. Because as we studied that this intercept is xd by r plus 1. So similarly, this intercept will be equal to xd by r plus 1, but in this case, r will be the minimum reflux. So you know the value from the graph of the intercept, okay, and you know xd, so you can solve it for r minimum, and you can report the minimum reflux ratio. Next, you need to find out the overall tray efficiency. Okay, we know the actual number of trays is in this in our column. Tray column is there are 11 trays. Okay, you find out the theoretical number of trays. There are basically 10 trays, plus we have a partial reboiler, so total 11 stages. And the theoretical number of trays, you find it from the graph, and then you find the efficiency. Number 8, we need to find out the heat removed in the condenser. So for this, we will use very simple relationship, Q equal to mCp delta T. We know the volumetric flow rate, around 20 liters per hour. You convert it to mass flow rate. We know the Cp, you can assume it constant because the temperature range is very small. And we know delta T. So the temperature, you see, inlet temperature around 35, the exit temperature 37. So you can find out the heat removed in the condenser. Similarly, if you want to do the calculation, you can do it for the this is for the bubble cap column or the tray column, and we can do the same procedure of McCabe-Thiele diagram for the packed column. But in this case, instead of number of trays, they are virtual number of rates, and we can find out the height equivalent HETP of theoretical plates, and you can compare the two columns. Okay, you can compare them based on the separation and other as asked in your data analysis. Okay, I think that's all, and thank you so much.